Hello and welcome. This video is on the human circuit activity that you did in class recently. In this activity, all of the students represented a quantity of electrical charge. We chose a coulomb of charge because a coulomb is the standard unit of electrical charge. A coulomb of charge, which the unit symbol is C, so you can see there I've written 1C, that means 1 coulomb. A coulomb of electrical charge is equal to 6.2 times 10 to the power of 18 electrons. So I've written that there, that's 62 followed by 17 zeros. That's a lot of electrons. I think it's about 1 electron for every grain of sand on the world's beaches. So there are a lot of electrons in a coulomb of charge. So to explain the human circuit activity, I'm going to use this circuit, which I made using PHET, which is P-H-E-T, Circuit Construction Kit. So you can Google that and download the PHET Circuit Construction Kit if you like, and you can make your own circuits and explore their behavior. The reason I chose this is because, like our human circuit that we did in class, you can see the individual charges moving around the circuit through the components, and we can learn a lot from that. So what I'm going to do, I'm just going to break the circuit using the switch. So this is, I've put a switch into this circuit so I can, what that does is it opens a gap in the wire, so we no longer have a continuous loop of wire, and as soon as we have that gap by opening the switch, the charges stop moving. Also in the circuit we have a 50-volt battery. It has no resistance. We have a light bulb, which we're going to say has 100 ohms of resistance, and we have a resistor with 100 ohms of resistance. So there's a couple of things to notice. Firstly, the density of the charges doesn't change whether the circuit is closed or open. The charges are always present, and they're always present in the same quantities. The charges in the wire are balanced, so there are the same number of negative charges as there are positive charges. So the wire is electrically neutral whether the circuit is closed or open. So each one of these charges we'll consider to be a coulomb. This is a 50-volt battery. So what does the battery do? Well, when the circuit is closed, the battery provides energy to push the charges around the circuit. The way it does that, just backing up a bit, many people think that batteries store charge, probably because we say in everyday language that we charge a flat battery. But when we do that, we're not putting charge into the battery. What we're doing is we're putting energy into the battery. And the way that that is done is through separating the charges in the battery out. So we create a charge imbalance in here when we charge a battery, and we end up with a surplus of positive charges on the positive terminal and a surplus of negative charges on the negative terminal, and those charges want to be reunited and rebalanced. So if we connect them up, the opposite ends up with a piece of wire, then those charges, because they want to be rebalanced, will move and push the other charges in the wire around to balance them out. So this battery is a 50-volt battery. What that means is that it will give 50 joules of energy to every coulomb of charge that passes through it. So the charges that enter, we're going to consider a conventional current, so we'll consider these charges to be positive charges moving. So as the charges enter the negative terminal of the battery, we consider that they have no energy, and then when they leave the positive terminal of the battery, they have 50 joules of energy per coulomb of charge flowing through. So if they have 50 joules of energy each leaving here and none here, then conservation of energy means that they have to lose 50 joules of energy as they move around the circuit. So there are two components in the circuit where they can lose this energy. So we consider that wire has got no resistance. I mean, in reality it does have a very tiny amount of resistance, but in high school physics we'll ignore that. So the charges will lose some energy as they pass through the light bulb. That electrical energy that they have is transformed into heat and light. Obviously with a light bulb, more light, less heat. They also will lose some energy as they pass through this resistor. The electrical energy will be transformed into heat here. The switch has got 0 resistance, so there's no energy lost there. Okay, so they have, each charge has 50 joules of energy to lose. Now the way it works is that if this is a 100 ohm resistor and this is a 100 ohm resistor, then they will lose half of their energy at this one and half at this one. So 25 joules of energy will be lost here and 25 joules of energy will be lost here. If we only had one resistor in the circuit, for example, say we only had the light bulb and this component didn't exist. In fact, why don't I get rid of it? I'll remove it. So as soon as I remove it, the circuit's broken, so the charges stop flowing. If I close the circuit again, the charges move and we can see that the light bulb is brighter. So the battery's still giving 50 joules of energy to each coulomb of charge, but now there's only one component in the circuit to where the charges spend that energy, and that's the light bulb. So now 50 joules of energy is being spent or lost, I shouldn't say lost, sorry, of electrical energy is being transformed into light and heat at the light bulb. So instead of 25 joules, now 50 joules. So more energy, more light. So that's why the light bulb is brighter now. Okay, in the human circuit activity, or at least in the worksheet associated with it, there were some questions asking you to say what was the electrical potential difference across different components. So firstly, electrical potential difference is voltage. So what we're just talking about is a difference in the electrical potential between two parts of a circuit. So voltage is always measured as a difference. You can't have the voltage at a point. You can have electrical potential at a point, but you can't have a potential difference at a point, and it's the potential difference that is the voltage. So I'm going to use this instrument, which is a voltmeter, to measure the electrical potential difference between one side of the battery and the other. Now, what do you think it will be? I'm hoping you said 50 volts. It's a 50 volt battery, so we should have a potential difference between the terminals of 50 volts, and we do. So now in this simulation, the wire, I've set it to have almost no resistance. So the wire does have a little bit of resistance. So over a long stretch of wire, some energy will be lost, but over a short stretch, not much. So if I look at the electrical potential difference between these two parts of this short length of wire, it's 0 volts, which is good. Right, so if I have got 50 joules of energy being given to each coulomb of charge passing through the battery, we earlier said that half of the energy will be spent here and half here if they've got the same resistance, which they do, they're both 100 ohms. So we should expect the electrical potential difference across the light bulb to be half of 50, which would be 25, which it is. Now it's negative because the charges are gaining energy as they pass through the battery and losing energy as they pass through the light bulb. So we could also do the same here, and we can see that there are the electrical potential difference across the both components is 25 volts each. So that means that 25 joules of energy are being lost for every coulomb of charge that passes through each of these components. So now if I remove the resistor from the circuit, okay, now let's just check that we are, so obviously still hopefully 50 volts between the terminals of the battery, and we should have very close to 50 volts being, okay, so 49.999. So obviously there's a, because the wire has got a tiny bit of resistance, we are losing a very small amount of energy around this longer stretch of wire. So there we go. So the battery is providing energy to the chargers, the energy is being lost in circuit components, and it's possible to estimate the amount of energy that's being lost in each of the circuit components. So we'll be doing a little bit more on this in subsequent videos. So until then, see you later.